All right, we're going to talk chemical reactions in this unit. In 7.1, we're just going to introduce chemical reactions, and we want to take a look at ways that we can write chemical equations that will actually describe these reactions. So first of all, let's talk about what a chemical reaction actually is. The reactions that we're going to talk about involve just a rearrangement of atoms in the reactant compounds to form new things. Those things are typically called products. There's a couple of things to keep note of when you're thinking about chemical reactions. The law of conservation of mass and the law of conservation of energy are always observed. So we want to make sure that those things come out at the end of the day. Energy from chemical reactions can be released, which is pretty common, but it also can be absorbed. This is what differentiates what's called an exothermic or endothermic chemical reaction. And chemical reactions, for the most part, result from just simple electron transferring between atoms. Chemical reactions are often indicated by a couple of different observations: the emission of light, heat, smell, effervescence, sound, and change of state can all be indicators of chemical reactions. Now, there are others as well. Color change, as you see to the right, the two solutions, the red and the green solution from the burettes above, are being added to form a bluish-purplish solution. That color change also is an indicator of chemical reaction. Now, each one of these doesn't necessarily have to be an indicator of chemical reaction. When you open up a soda and you hear the fizzing and you kind of pour the soda into a glass, you'll see effervescence, you'll see bubbling, but that isn't a chemical reaction. That's just the gas being released from the liquid itself. So usually when we're trying to see if a chemical reaction is occurring, we want to see more than one of these indicators to be sure that there is a present chemical reaction. In math class, we use equations to kind of define a process that we're doing, and we'll do the same thing here in chemistry class, but our equations are a bit different. They're called, obviously, chemical equations. Chemical equation is a symbolic representation of a chemical reaction, and I'm going to give two examples of chemical equations today. The first one is going to be something pretty common that you maybe have done it's going to be the old baking soda volcano chemical reaction. So we've got a couple of compounds. We've got sodium bicarbonate, which looks like this, and we've got acetic acid, and that looks like this. And those two things combine with one another, and they're going to make some new products. Back that up. All right, they're going to make some new products. I want to get rid of move my arrow here for a second. There we go. Okay, I'm going to put my products in red here. So the three products that they're going to make, you're familiar with two of them. One is carbon dioxide gas. That's the gas that's evolved that gives you the bubbles. The other one is water. And then the third one, which you might not be as familiar with, is just sodium carbonate. So that looks like this: Na2CO3. Okay. Now let's define some things about a chemical equation. The stuff in the red, we call that stuff a product. That's being produced. That's what we have left over at the end of the chemical reaction. The stuff in the blue, we call those things reactants. The yield arrow is the arrow in the middle that separates products from reactants. If we have a catalyst, like I did in the demonstration today with the potassium iodide, we put the catalyst on top of the arrow, because a catalyst isn't used in a chemical reaction. It just speeds up a chemical reaction. Okay? So there's a couple of definitions that we want to know, that we want to take to heart. All right, let me go over a second chemical reaction now. You're also familiar with this one. We take some iron, and we're going to add oxygen to the iron. And we're going to let that sit outside for a little bit. And we're going to form a new compound, and it's going to be called iron 3 oxide. Again, we have the products in red and the reactants in blue. We have the yield arrow in the middle. The one different thing about this chemical reaction is that it is not currently observing the law of conservation of mass. If you look on the left side, we've got one iron atom, and on the right side we've got two. And then also the oxygen atoms are wrong. So we want to fix that. I'm going to attack the oxygen atoms last. You'll find out that saving oxygen and hydrogen for the end are often a good idea. So let me just use green for coefficients. Coefficients are numbers that we put in the front of compounds or elements to actually change the total number of compound or element molecules that we have. So if I put a 2 in the front of Fe2O3, that means that I've got 2 Fe2O3. So in total, 4 iron atoms and 6 oxygen atoms. Again, that's a ratio, because if we think of Fe2O3, it's an ionic compound. So there's actually maybe like, if there was a 1 in front, that would be like 2 billion irons and 3 billion oxygens combined together. Now that there's a 2 in front, it doubles everything. It's a ratio, so it works. If I have 6 oxygens now on the right side, I'm going to put a 3 in front of my oxygen there to get 6 on the left side. And then a simple 4 in front of the iron to make it 4 irons. So again, these green things that I've got here, they have a special term, they have a special name, and those are called coefficients. Okay. One thing to take in part and to take note when you're working with coefficients is that if you're going to be asked, well, how many iron atoms do I actually have? You have to multiply the iron subscript by that proper coefficient. Okay. Let's see. That's good for now for chemical equations. Now the last thing that we'll talk about with the chemical equation is that we often want to tell the reader what the phase of the product or the reactant is. So a proper chemical equation is going to actually do that. And if we had some oxygen, we normally wouldn't just write O2. We would tell the reader the phase that it's in. So parentheses follow the O2, and then there's a G inside of the parentheses. That means that we've got oxygen gas. We do the same thing for a liquid. Obviously that would be L, and for a solid we'd have S. But there's one last phase that's really kind of confusing, and it's probably the most used phase in a high school chemistry course, and that's AQ. AQ means aqueous. So if you see NaCl with parentheses AQ, that means you have aqueous sodium chloride. This means that the NaCl is actually dissolved in water. So if you were a really little person and you could see the beaker, maybe that's your beaker, and you could swim inside of there, you wouldn't have combined NaCl. Instead, you'd have Na with the plus charge, and you'd have a separate Cl with the negative charge in a 1-to-1 ratio floating around inside solution. So to denote that, we use this little AQ after that particular compound. Water is not necessarily part of the reaction. So we could say NaClAQ plus, lead iodide, PbI2, and we'd have stuff on the other side. We'd have products that would be formed, and water itself would never be written out. That means that water doesn't participate in the chemical reaction. It just allows things to dissolve. Also, you often hear the term like a salt solution. If you hear that, that means that it's aqueous. So salt solution would still mean NaCl aqueous. Now there are going to be times where I ask you to omit phases for brevity. We want to just write a lot of chemical reactions, so I don't need the phases. So be sure to read instructions on worksheets or ask, hey, Mr. Cornick, do I need to write phases for this thing? Okay. I want to do one final chemical action. And I want to include the phases with this particular chemical reaction. Let's go copper metal. And let's add that copper metal to, let's say, potassium nitrate. Potassium nitrate is going to be aqueous, so I'm going to put an AQ after it. And we notice that the copper metal is solid. I react these two things, and then on the other side, I get the potassium all by itself, plus copper nitrate. Now actually this reaction wouldn't occur because potassium likes to be with nitrate a little bit more than the copper does, but just for argument's sake. So copper 1 nitrate we'll say is formed. That now is aqueous. So you might ask, well, Mr. Kornick, how are we going to know if something's solid or aqueous? Well, sometimes we'll be in the lab and you'll be able to visualize if it's solid or aqueous. On quizzes or tests, on the other hand, you'll actually be given that solid potassium or aqueous potassium nitrate. And so you'll be able to write that out. Okay? So there you go. That's writing chemical reactions.